All right. So, okay, hard question one. It's quite pretty funny since I was getting back into making that YouTube video for Leetcode. And Leetcode keep giving me hard question. Anyways, it is what it is. Okay, to the Leetcode question is a minimum 1-bit operations to make integer 0. So let's see like we are given a integer which is the ends in a parameter. We have to transform it into the 0 using the following operation in any numbers of time. So that means we are allowed to do the two operations here. So if we really read through it, it's quite confusing. It even took me like 5 or 10 minutes to really understand. So what we need to do is just we need to return the minimum number of operations to transform the input n into the 0. So let's go through in the example here. I have prepared some. So to really understand the do clause which is given here, so we are allowed to change the right mode 0 bit in the binary representation of n. That means if we are using the binary version of 3, that means 0. Why is it so small? All right, let me try to make it a little bit huge. All right. So we have 3, which is will be the something like 0, 0, 0, 0. So let's consider this is a binary version of 0. So I'm representing it in 8 bits integer. That's why there's a 8 0 in here. I'm missing one. Silly me. Okay. And then I'm gonna subtract like this for easy to read. Alright. So next step, what we need to do is we have 3 given in here. What do? We're gonna use it 1 in here, 1 in here. Since we are using the 2 power of everything is in here, which is a 2. So in here, 2 power of, I think is going to be the 0, 1, not from the, okay, it should be there like this, 0, 1, 2. So if I have to mention like this, that means this is a power. So 2 power 0 is 1. Let's write like 1 here. And then 2 power 1 is 2, which make us create the 3, which is the decimal. So if we really have to describe that values in here, it will be the 1, 1, which is the binary, and decimal that will be the 3. So in this version, how are we going to do? We are going to exchange the right most. Okay, let's forget about the 3 in here. I'm only described in the binary integer. Okay, so for the class 1, which is given in here, that means we can easily change the rightmost of the binary representation, whatever we want. So in leftmost in our side is here. So we can swap this to 0 or 1, whatever we want. But our goal is to make the this 1, 1 to begin the all 0. That is our goal. So 1, 1 is a 3. So we totally need to forget about the decimal value at this time. So how do we do? So I have explained the first clause. So for the second clause, I can explain. How can I explain? So just a side joke. The question is something like this. Let's say you are the Mr. Swift, and then you have one girlfriend. The question they want to know is how many kids you have. The answer is no, because Mr. Swift have not married yet. That is the answer. So the same for the clause, the second clause that they provide them is quite not straightforward. So change the I bit in binary representation of n if I of minus 1 bit is set to 1 and I of minus 2 bits through 0 bits are set to 0. So before moving that, I can explain what are the value points to change or flip the bits in second class. Let's create the numbers in here. Let's say we have 100. So 100 means like 2.0, 2.1, 2.2, which is the 4 in decimal, but we totally forgot about the 4. So we want to change this integer, leftmost integer, leftmost bit, not integer, sorry about that. And then how we can change it? We're gonna change it. The reason why I minus 1, let's call this is I, minus 1 is set to 1. Since this bit is not 1 and this bit is only 0, we cannot change this bit into 0. It's pretty straightforward. Alright, the second example. For the second example, let's use like we have a number called 0, 0, 1, 0, which is 2 in decimal, but we don't need to think about the decimal in our case. So I want to change this leftmost bits from 0 to 1. Can I change it? So according to the second clause, so this is I, and then I minus 1 is set to be 1. So this is value point, and then I minus 2 through 0 are set to be 0. This is valid. So both clauses are satisfied in this area, so we are allowed to swap and flip that bit of the left pole into 1. Alright, this is the second example. And third example, for the third example, I will say like, let's go, we have 0, 1, 1. We want to change the leftmost bits. So currently, every example I'm providing is only for the class 2. Since the class 1 is very straightforward, the rightmost 0 bits in the binary position can be flipped whatever we want, like from 0 to 1, 1 to 0, and vice versa. And then for the leftmost bits, what do we need to do? We want to swap and flip from 0 to 1. So we check our I minus 1 bits, which is set to be 1. This is a value point. So I minus 2 are not set to be 0, which is 1, which create as the invalid. So we can flip the leftmost 0 bits. No, we are not allowed to flip it. This is for example 3. I also have a better, great example. Okay, the most intuitive part will be the, let's call it, we have something like this, which will be the 0, 1, 2, 3, 4, 16 in decimal. So we don't need to think about the decimal in our case. So this is just that leftmost is a 1, and then we want to flip through it. So this is the i's in our case. So we check I minus 1 is here. So which is need to be set to be 1. So that is invalid in our case. And then next I minus 2 is set to be 0. So which is valid. That means we only verify the only one case for the class 2. In that case, we are not allowed to flip the leftmost bits into the 0. Right. And then, but there's a one case, in case if our bits in here is 1. Right? So if the bits in here is 1, are we allowed to change it? Yes. Why? Okay. Why? So this is 1 in here, 0 in here. We are allowed to swap the value of x in here. Let's call that we have a 1 bit in here, whatever, like 1 or 0. We are allowed to flip that number since we have I minus 1 is set to 1 and I minus 2 is set to 0. Alright, so enough explanation for the class 2. So for this case, in here the explanation, the binary representation of the 3 is 11, which I in here, and then so we check like the 1 1. So they check like 0 of 1 with the second representation, since the 0 bit is a 1. So they mention like 0 bit is a 1. That means 0 bit mean like leftmost is 1. Okay, I have to arrow point to this side 1. But we will check like I minus 1 is 1. That's also true. But where is the missing 0? So we can think like everything filled in here are marked as 0. That is why we can flip that 1 1 into the 0 1. So we flip the leftmost since it is match with the second clause. So we flip it, and then the rightmost, so we match with the first clause. That's why we flip that into the 0 0. So how many steps it takes? 1 2. That's why the answer in here is 2. So enough for explanation. And then for the asymmetry 2, it is the same, but I will not dry run the asymmetry 2. You guys can try it out, and if you don't have a clear explanation, you can leave a comment. I try to come and explain it again. So let's try to solve it. How do we solve it? This is a little bit of a mathematical theory behind the scenes. Let's say like, let's check the clause. So that means the n can be 0. So in that case, let's call, if we have n become the 0, we just return the 0. Since it is a 0, there's no way for us to flip the input parameters to make it 0, since it's already 0. So what do we want to do? We want to calculate the highest bit. Let's call like highest bit. So calculating the highest bit mean like we want to check the how to say, check the what is the highest bit in here, like the leftmost bit in our case. So how do we check? Okay, that's pretty straightforward. I'm gonna need to calculate like integer of bit width. So if you guys don't know what is the bit width mean, I have a Swift Rebel open here, so I can represent the video for you guys. That is should be the width. Sorry, my bad. No, bit width. So that represents, since it is a 64 bits architecture CPU, so it show the 64. Let's call that we are using the integer 8 dot bit width. That would be the 8. The same for the integer 16 will be 16. So that represent these kind of binaries in here. And then what we want to do is we want to detect the leading 0 bit count. So what is a leading 0 bit count? Let's call it that we have a integer 8 of how do we say, 31 of bit width. That means we have 8 bits with the here, which is 8 bits, and I want that 31. So to get the 31, just Google it. 31 integer in bits. So if we check in here, so let's convert the binary 31. So that is like this in here. Let's use like this. So the reason how we get the result in here is 8. So because how I get the 8 width, because I'm just checking the bit width of 31. That means 8 bits. And then I want to know is the leading 0 bit count. Let's call like leading 0 bit count. In that case, that will be calculating the total number of 0 in integer 8, so which is a 3, right? So but we are using the leading 0 bit counts from here. This is the asymmetry from Apple, and then if we are detecting it, that means we are detecting the 64 bits in here. So the great example would be, let's go like we have a 64 bits integer, and then we have a 3. 3 is 1 1 in binary. That means 64 minus 62. Let's call it like, let's calculate like 3 of leading 0 bit count. That would be 62, because 3 is a 1 1 in binary, and if we deduct the 2 from 64, that is making them 62 for us. So that's what we're doing here. And then what I want to do is I want to shift the bitwise left shift operator to 1. So if we shift like this, what is going to happen? So we're going to shift everything. Let's say like we have a 0 0 1. If we create an operation like 1 to the 0 0 1, that will be the 0 1 0. We just shift the 1 bits to the left. But in here, we need to detect the 1 since we are using the 0 base index, and then that's why we need to detect the 1. So next step, what we need to do. So we have done for calculation, and I want to check the. Okay, I think I can just write down by using the recursive. So what we need to do is we need to find how many bits the number used. So how can I search? It's also very straightforward. Just by using the bit width, should be the bit width minus n dot leading 0 bit count. So now what we want to do is we want to check how many bits the number used. The numbers mean the input number, and then we want to shift that into the 1 bit. Let's call it like 1 bit move here, and then we still need to detect the -1, which is we check the how many bits we actually use as the highest for the number inputs. And then what we need to do is we just recall this function again, the recursive. Inside that, I'm going to use the XOR operator. If you guys don't know what is the XOR operator, so let's say it's like you have a 0 0 in here. So XOR means if it is both the inputs are the same, that means it's going to create the difference for you. So I think I will think about it like, let's say you have a 0 0 and then 0 0 1 and then 1 0 and 1 1. So after that we have this kind of thing. What we can explain to you is I just want to explain like how is XOR operator works. So for the XOR, so that is like if two inputs are same, that's going to return the 0. If two inputs are not the same, it's going to return the 1. That's why it's called XOR. Alright, let's get back in the BizNet. And then what we need to do is we need to use the XOR operator, and then we will use like N XOR with the highest bit, and then we can just run through it. I think I can do something. Okay, I think I can just operate like this, called the bit length, and then I can remove this from here. So I will be replacing all the subtraction with the bit length. Let's call it this a bit length, and then this will be the bit length, and then -1, and then minus into the. Let's try again. Okay, let me think. What did I do wrong? Highest bit. Okay. Oh my god. complexity will be the log n, if I'm not wrong. Alright, it's pretty efficient. I think nobody solved the question very deep for the hub. And then that time complexity will be the log n, and then the space complexity will be the O of 1, since O is log n, since we are calling it recursively, so this is using the space. Alright, that's all for today, and see you in the next video.